3, 2, 1. Okay, this is part 2 of the definite integral. In part 1 of this video series, I talked about the definite integral and the formal definition of the definite integral. And we defined the definite integral as the area under the curve. So we have this curve here, and we can block off rectangles like so, and add up the area of each of those rectangles for an estimate of the area under the curve. And if we increase the number of rectangles, alright, we can estimate more closely, alright, the actual area under the curve. And if I take the number of rectangles, alright, n, and I let n go to infinity, that is, I let the width of this rectangle become infinitely small, as I gain infinitely many rectangles, I will fill in the area under this curve, and if I take the sum of that, then I will have the area under the curve, and that was our definition of the definite integral. Alright, and so far we've only dealt with functions that sit above the x-axis. And when we deal with functions above the x-axis, let me come over here to where the rectangles are wider. When I take that x sub I that we saw in the last video and I evaluate it at the function, I'm going to get a positive value. Something different is going to happen if the function sits below the x-axis. So if I have a function, maybe part of it sits above, part of it sits below, when I go to take my rectangles and I evaluate my rectangle, say my xi sits here, now my xi is negative, which means when I take the area of that rectangle, the area of that rectangle is going to be negative. So I have to be careful when I'm evaluating the definite integral on functions that sit both above and below the x-axis. I need to think about what's going to happen. Alright, so if I want my area to actually represent an area which is going to be a positive value, then when I take the definite integral, I have to split it up. I have to take the part that's above the x-axis, which is going to be positive, and I take the part that's below the x-axis that's going to be negative, and I take the part that's above and I subtract the part that's below, because by subtracting the negative, I'm really adding the two areas together. So that's something to keep in mind anytime you're asked to find the definite integral, that you graph your function, make sure the form that your interval takes. Okay. Alright, now some properties. Let's look at some basic properties of the definite integral before we look at how to actually evaluate it. Alright, there's a couple of things we can look at here. First of all, with the bounds. If I have an integral that's being evaluated from a to b, and I swap the bounds, so instead of going from a to b, I'm looking from b to a. What am I doing? I'm reversing them. So instead of going this way, which is my positive direction, I'm going this way, which is my negative direction. Right? So when I evaluate one of these definite integrals, alright, from a to b, I get a positive area. If I swap the bounds from b to a, I then have to negate that, because b to a is going to give me a negative area. Alright, so basically when I swap the bounds, I negate my definite integral. Alright, or I take the opposite of it. I shouldn't say negate, I take the opposite of it. If I look at a definite integral that's evaluated, now in this case from a to a, alright, we don't take an actual width. Alright, I'm just looking at this line segment here. Alright, and a line segment has no width at all. So if my rectangle has a 0 width, then my rectangle is going to have a 0 area. Right? And then the last one from this set that I want to look at is what happens if I take an interval from a to b, and then I take some point in between c. Take some point in between c. I can then look at my integral in two parts. I can look at it from a to c, and then I can look at it from c to b, and then I can add those two together. Alright, so I can take a point that sits in between a and b, and I can use that to split my integral up into a sum. Now where that comes in handy is back over here, alright, because we would use this as the c. So in order to evaluate an integral that looked like this, I would split it up. I would take the integral from a to this point here, we'll call it c, and then I would take the integral from c to b, and I would put them together using my little form here which says I'm going to subtract them because this one is below. All right. All right, and then finally, before we get into evaluating and examples, all right, let's go through some basics now. The integral follows a similar set of rules as we saw in the last time we met with the antiderivative. All right, don't worry about the first one for right now because I haven't gotten into how to evaluate that, so we'll skip that one for now. That's not really one of the fundamental rules anyway. All right, if I have a constant times a function, I can pull the constant outside the integral just like I can with the antiderivative. If I have the sum or difference of two functions, I can split my integral up into the sum or difference of the two integrals, just like I can with the antiderivative. All right, here's the rule about splitting, finding that point in between and splitting the integral up that way. Now I can bound, all right, if I have two functions that are positive, all right, and I have one function that's larger than the other for all x in the interval, all right, in this case we have g is larger than f, then I can say that the area that g bounds is larger than the area that f bounds. That kind of makes sense. Here is, again, the other fundamental rule about just evaluating at a constant value instead of an interval, and the rule about negating the integral. All right, now in the next video I'll go into the first fundamental theorem of calculus, which allows you to actually evaluate a definite integral.